versus, I mean, I told you, I get militaristic, it's an assassination is what it is. You know, so I have a receptor that is specific to Salmonella enteritidis, and this is what I'm gonna target with it. I have a receptor that only responds to Staphylococcus aureus. That's how specific the adaptive immune response is. Who are the cells involved with this? Yeah, T cells and B cells is the crux. What big heading do they fall under? Lymphocytes. What percentage of circulating red blood or white blood cells are lymphocytes? 30. Are you sure?
Yes.
30, because we know our mnemonic, right? Right. Are all lymphocytes leukocytes?
Yes.
Yes. Are all leukocytes lymphocytes? No. All right. So the things that we're looking at with adaptive immunity, specificity. That is the key. You are going after a particular target. The other thing is inducibility, which is a little, I don't know, it's a little misleading because you think an innate system is inducible as well. But what you see with the adaptive system is more clonality. So when a particular cell is, you know, I have the receptor specifically for Staph aureus. When that receptor gets triggered, then you start cloning additional cells that have the same exact receptor. So that's what inducibility and clonality refer to, unresponsive to self. This is key. What happens if you have immune cells running around targeting self cells?
Autoimmune diseases.
You've got autoimmune diseases, which can be very, very, very serious. So you want to make sure that you're selecting cells that are not going to go ape, you know what, with your own cells. And then memory. Innate systems, innate cells, innate responses don't really have memory because they're not specific in the first place. So these are the key things with adaptive. And of course, we're looking at T cells, B cells. Where do those cells originate?
T cells are in the thymus.
They both originate in the bone marrow.
Right.
They start in the bone
T
marrow.
mature in the thymus.
Yes, the T cells mature in the thymus. The B cells mature where? Still in the bone marrow. Still in the bone marrow. So we're going to look at two types of adaptive immune response: the T cell response and the B cell response. I mean, in a nutshell, that's what it is. The T cell is cell mediated. The B cell is antibody. So there's your division with your associations there. Do we need to get into this whole lymphatic business? I'm not going to ask you for specific lymphatic structures. You definitely need to distinguish between primary and secondary lymphatic organs. What is the distinction between those two, based on what you know? Yeah, good, Maureen. The primary is where these cells are originating and maturing. The secondary is where they're hanging out. So the red bone marrow and the thymus, that's the police training academy. The lymph nodes, spleen, tonsils, whatever, that's the communities they're hanging out in. Okay, so we'll keep that analogy going throughout. Why do you have more afferent vessels leading into a lymph node than efferent?
Garbage is coming in and then cleaning.
Yeah, essentially, because the lymph system, the spleen, the malt, what's malt? Mucosal associated with it. What's malt?
Did you say it with a B or a B?
A B.
That's the ones in your gut, right?
So that's malt. Vault is bronchial. Bronchial.
Oh, very nice, yeah.
Yeah, you got it. There's all, how many body regions are there with a B that you need to screen? I mean, really. All right. Anyway, the point is, all of these secondary organs, including and especially the lymph nodes, these are areas where all of the body fluid passes through multiple times per day. They are ideal places for immune cells to be hanging out and screening that material. So that's the deal there. So what exactly are we screening for? What are we looking for? I'll give you a hint. It's right there. Yes.
I didn't hear what Marta said about the current version.
Oh, do you want to tell her again? Okay. Sorry. No. She said correctly that you have multiple vessels going in and fewer coming out to ensure that the fluid stays in there long enough for inspection before it's sent out. So it flows in faster than it flows out. And she used words like garbage and cleaning and inspection, which were all correct. Nice. All right. So we're screening for antigens, which is a special, it's typical of any pathogen. You can make the distinction between the two, and there is one, but I tend to use them interchangeably. All right. Front door, they warned us about this. Go out, let's just go out. It does feel better outside. Who stopped and did this before? No, it wasn't. Somebody stopped and drew this picture, and now this guy he got burned up in the fire. Okay, so antigen.
Scarier.
Yes.
He looks like Redbeard the pirate.
Okay. Antigens.
What did you say they were screening for? Like, you said they're screening for something?
Yeah, antigens.
Oh.
I
Okay.
use the term pathogen, Jesse.
Okay.
And there is a hair's width of a difference between the two. I tend to use them interchangeably.
Okay.
A pathogen is anything that can cause disease or symptoms or changes your physiology. Antigen literally means antibody generator. So it's something that elicits an immune response. Sometimes antigens are different for some people than others. For example, who is currently bothered by the pollen? You know what pollen is, don't you? Oh, y'all don't know. We're gonna have a little bit of a lesson in general biology right now. Pollen is what does it mean when one plant pollinates another? It impregnates it. So pollen is plant sperm.
Nice. Yes.
I didn't ask for this, so technically I'm being raped by trees right now.
Don't worry, I got that.
Y'all need to turn these phones in. It's true. It's very true. It is plant sperm. All right, so antigens. Antigens elicit an immune response. They can be allergens. So it's not necessarily a disease-causing agent. It's something that causes your immune system to respond, whether rightly or wrongly, as is the case for allergies and so forth. So if you recognize an antigen, you recognize it based on certain characteristics that it has. We introduced an acronym for certain determinants that help the innate immune system recognize invaders. What was the acronym? When we talked about innate immune system, we were talking about ways that some of those innate cells can, like complement, can recognize invaders. And the PAMP was the acronym. PAMP, oh yeah, we made sure you did. What does, this is funny, what does PAMP stand for? Pathogen-associated molecular pattern. It's a series of molecules, can be sugars, proteins, glycoproteins, which is a sugar protein, various repeating sections that clue those innate cells into recognizing, all right, this is not supposed to be here. Certain things that are typical of certain bacteria. There are two that stand out in my mind. What's the number one identifier for bacteria?
their cell wall.
Their cell wall, which is made of
Peptidoglycan.
peptidoglycan, and then there was one other thing that we mentioned that our cells sort of have too, or some of our cells do, but the structure is different in bacteria, and it was flagellin.
Yeah.
Flagellin, because we don't have flagellated cells.
Right.
I mean, Mikey does, that's it. Right, well, you get the idea. We don't have cells with flagella. Bacteria frequently do. So and their flagella, because their prokaryotes are structurally different, those chemicals can clue in the immune response. So in that way, those molecules are similar to antigenic determinants. So an antigenic determinant is the one thing that determines who that pathogen is, just like facial recognition for that matter. So if I see somebody who has, sitting in this particular seat, so I recognize a person sitting in this seat, pretty ladies all the time asking me questions and reminding me to do stuff. I know it's Maureen. If I hear a loud voice from that corner asking me for bonus points, I know it's Jamie. Y'all see somebody up here with a big mouth making stupid jokes, you know it's me. The point is, each antigen has a characteristic that is unique among antigens. So that's how your cells recognize it. Sometimes the determinant is referred to as an epitope. It is the recognizable characteristic, and each antigen can have multiple ones. Why is that a good thing? Our immune cells. Why is it beneficial for us that each antigen can have multiple epitopes or multiple determinants? Yeah, because the more determinants it has, the more likely we are to have a cell that recognizes it. Which part of our immune cells recognize the determinant?
A receptor.
Has to be a receptor, and I'm going to keep drumming this home because the receptors are key. So what determines whether the receptor matches the epitope? Not MHC yet, it's just simply the shape. It has to be like a physical lock and key. So on this one, you've got an antigenic determinant that looks kind of like a square, one that's kind of circular, and one that's pointy. Those receptors have to be shaped the same in order to bind to those determinants. Does that make sense? What then determines the shape of the receptors on your cells?
Your antibodies?
Not your antibodies. Well, what is a receptor?
Before.
Necessarily. What kind of molecule is a receptor? They're proteins. Therefore, what determines the shape of the receptors? It's DNA. It's DNA. So it is purely by chance, with that initial encounter, purely by chance that you have a receptor that matches that determinant. Now, on later exposures, yes, you will deliberately produce cells with that particular receptor. But with the initial response, you either get lucky and recognize it or you don't. And it attacks. It still may attack. But the point is, you have multiple, how many different receptors do your cells produce? Or how many different receptors can there be?
A lot.
More than we can even fathom. Each type of immune cell only has one, but because we are so diverse, there's a very good chance that you're going to have a receptor that matches one of those determinants. Do you see what I mean? Everybody good with that?
So the people that are allergic to like everything, they just were born with more receptors, like more.
It's not necessarily in that case the receptor, it's the inability to distinguish what response is appropriate. So my husband, who is one of those genetically inferior people,
Right.
he is allergic to everything. I've told y'all about his woes before. But when his mast cells encounter pollen, they go, bah! In other words, they kill the daddy long legs with a flamethrower. That's what it is. That's what an allergy is. When it doesn't have to. That's the difference. That's the difference. Our other people's receptors will bind and recognize and be like, you're not really a threat.
Okay.
All right. Are we good with this? Okay. So, there are various types of antigens. And this is important because these words are gonna come up again later, and if you remember your immunity from AMP2, these words will be familiar. Exogenous, endogenous, auto. Didn't do so much auto in AMP2. What is an exogenous antigen? Yeah, it's from outside the cell. It may be one that one of your immune cells has deliberately phagocytosed, but it was still outside the cell. An endogenous one, on the other hand, is what? It's inside the cell, but I want you to make this distinction. It's inside the cell because it has infected that cell. That cell has been infected. It has not deliberately taken in the antigen to try to eat it or whatever. That cell is infected. Okay, do you see the difference? And then an autoantigen must be what? Yeah, it's self. So your cells express antigens as well, but instead of eliciting the antibody response, they're there so that your immune cells know it's you. In other words, remember we talked about the natural killer cells? Which cells do they target? Tumor cells and virally infected cells. How do they know those cells are malfunctioning? Because the autoantigen, that external protein marker, is either not there or it's screwed up. And it is the MHC1. We'll get more on that in a minute. Yes?
So what kind of, a lot of antigens, does that mean really be like?
No. No. It means that you could still be infected. It just means you have a lot of circulating pathogen. And that just, so it's a matter of which immune response is being elicited by which. So both will elicit the response. Which is which depends upon if the antigen has infected the cell already or if it's just circulating. All right, you good? Okay. So then that brings us to antibodies. Good guys or bad guys? These are usually the good guys, and antibodies are there to do what? Yeah, antibodies, and this is a little bit not the same order we did in AMP2. Antibodies are the good guys. They are proteins that are secreted ultimately by plasma cells and B cells. So when you see B cell, think antibody response, because that's what they do. What kind of molecule is an antibody? They're proteins. Are they actual cells? No, and that's why, remember we said with T cells and B cells are a cell-mediated response, B cells are antibody-mediated, they're two different things. Antibodies have a similar structure, all of them. They're definitely Y-shaped, and what we're gonna see is that they are the same shape as the receptor of the B cell that produces them. They are the same shape as the B cell that produces them. They have constant regions, which is the stem of the Y. They're all the same. Notice where the variable region is. It's exactly where you think it should be. It's up here at the end because the variable region is what is looking to bind to the antigens on the foreign invaders. Make sense? Okay. Where have we seen an antibody response that does you harm? When you have mismatched blood types. And this always messes people up because you learn about antigen when you're talking about or type A, type B blood. Those are the autoantigens, whichever ones you possess. You have type B blood, what kind of antigens are on there? B. If you have type A, that's why I want to mention it because it's contextual. Type B blood has the B antigen. What antibodies do you produce? Anti-A. Anti-A. So as you develop, that antibody response to foreign blood types develops as well. So generally speaking, antibodies are good guys. They are proteins, and they have a constant region which is identical, and they have a variable region which is what does the binding. And they come from which set of adaptive immune cells? B cells. Good. There are multiple classes of antibodies, and we often refer to them as immunoglobulins. IgA, IgG, and I remember these as GAMED, G-A-M-E-D. So, you don't have to know the structures of these guys, but there's a couple of characteristics that you need to know. You need to know that the most abundant present in the system, or in your body rather, is IgG. On any given day, that's gonna be the one you have the most of. IgM is the first on the scene. So when you have a new infection, levels of IgM are gonna be elevated beyond the norm. The other thing about IgG, it can cross the placenta. It's the only one who can. It's the only one who can. IgG. Which makes sense because it's the most abundant, always present. Makes sense that it would be the one that would cross over to protect the developing fetus as well. IgA, if you were in my AMP2 class, I told you to put what word in front of that? Secretory. Always secretory. So where do we find IgA? Mucous membranes, tears, saliva. IgA is passed from breast milk to baby as well. That is a secretory process. So secretory IgA. IgE, I think eosinophil and allergies because that's what it does. IgE has to do with also parasitic infections. So its chemical mediator is probably what? Histamine. Good. It's not me to even do this. Y'all already know this stuff. IgD, we don't know what the hell it does. It actually is pretty poorly understood of the group. So the question is, who cares?
The person.
Marta's looking at me like,
Doctor. Your doctor.
Because the blood work would tell you what kind of,
Right.
your doctor cares because the blood work can, if you have elevated levels of particular ones, it can help them understand what you have going on. You present with, severe bronchitis and your eyes are watering and you're sick and you're miserable but you have no fever. You got a very elevated level of IgE. What do you got? You probably are allergic because you're being raped by the damn trees, right? but you get the picture. So different levels from the norm can tell you information. And I told y'all the story of my dean, right? Who is an immunologist. I mean, that was his baby as he was going through school. That was his favorite thing to study in his area of expertise. And when his kid was born, how would you like to have been the nurse in this situation? Was questioning the vaccine schedule, which is up for debate, but, took his baby to the pediatrician and asked specifically, with this vaccination right here, which class of IGs are you targeting? Which class of immunoglobulins are you trying to elevate? What? But the point was, depending upon if it's a short-lived, long-lived, is this the best time to administer this vaccine? And it's something that is worth discussing. We need more research in that area, but that's why. Yes? Yes, they do. Good question. Maureen asked, so since IgG crosses the placenta, are babies born with a level of circulating IgG? Yes, they are. And
Is that innate, or
Right.
is that innate or?
Oh, no, it's still considered specific. It's
Okay.
still considered specific because, you think the adaptive immune system is still developing, but look at what they're exposed to on the way out. And there's actually a lot of evidence to indicate that babies born vaginally versus C-section kind of get an immune boost because as they travel through the canal, they're exposed to more bacteria, lactobacilli and so forth, that they would not be exposed to if they're extracted.
It's that the innate
Yes.
Is that passive immunity or?
Good question. IgG to baby through placenta would be natural.
Natural passive.
It would be passive natural because
Not
baby is
active.
not producing it. But when baby gets a vaccine and starts producing their own, then it's active. And we'll get onto those in a little bit too. Are we good with immunoglobulin classes? What they are, what they do, and why? Yes? I think that they would have developed secretory IgA pretty soon, but I'm not sure exactly to what extent, because their immune systems aren't developed, which is why, again, breastfeeding is considered an immune booster because of the IgA. So, I don't know, I don't know the details, but I can find out for you. Okay, so we know what antibodies are. We know what their, we know what different classes and groups are. Now let's talk about what it is they do. We kind of have this idea that antibodies are destroyers, and they're not. They're, first of all, again, they're not cells. They're what? They're proteins, and so they can only do certain things. Basically, when I think of antibodies, I think of marked for destruction. Marked for destruction or neutralization, which is kind of similar. So they function a lot like complement proteins. They can neutralize a toxin or a bacteria by doing what? What are they doing up here?
Clog the receptors.
They bind to all the receptors and they clog them up. It's still present, but it can't bind to any of your cells to cause problems. Now, I like the fact that you're shown not just bacteria, but also viruses and toxins. What is a toxin? Something toxic? Yeah, so we think about toxins as poisons and whatnot, but there are many bacteria where the bacteria themselves are not making you sick, but they're producing something really nasty that is.
Like biofilm.
Like a biofilm produces toxins, like Staph aureus can produce toxins. Diphtheria. Y'all know what diphtheria is? We've seen a bit of an upsurge in diphtheria. It's a toxin. Botulism is a good example. What does botulism do? Y'all know what it is though, right? Where do you get it? Poorly canned foods. Botulism is Clostridium. It lives in the ground. It lives everywhere. So when you pick your green beans from the garden and you don't put them in the pressure cooker because you've got to be above 110, Clostridium forms an endospore. So if you have those green beans with your Clostridium endospore and you open them up after a year on the shelf, are they going to smell bad?
No.
No, because the boiling water produced an endospore. Put it in the pressure cooker, you destroy the endospore. All right, so that's where we are. Clostridium itself, not really going to bother you at all, but it will produce botulinum toxin, which blocks the acetylcholine receptors on skeletal muscle. What will that do for you? It is a paralysis, and it is a paralysis that's severe enough for you to die. So what they do is they put you on a ventilator and hope that your body can clear that toxin before you die. It's supportive care. Supportive care. But the point is, antibodies can target a single protein in the form of a toxin as well as the actual bacteria itself. So you can take all the antibiotics in the world and get rid of the Clostridium, but you're still left with that toxin. You see, so that's kind of bacteria that produce toxins are nasty stuff. Nasty stuff. So neutralization, which is similar to opsonization, and opsonization literally means what? Make it tasty. This is the chocolate covering on the strawberry, right? So antibodies cover the invading organism, and that's the mark for destruction in my mind. So not only does it make it easier to phagocytose, it makes it easier to find. Oxidation. What's going on here? Why are some bacteria anaerobic? Or what does it mean to be anaerobic? Yeah, remember back in chapter, I think it was 4, when we talked about certain forms of oxygen that are toxic. And I think of oxygen as being a very caustic kind of a molecule. It's just one of those things because it's so electronegative, it starts pulling and stripping electrons off of the other elements. And that's what makes it toxic. So some bacteria are highly sensitive to that, and some antibodies can cause oxidation. So it triggers the formation of hydrogen peroxide, which kills the cell. The other thing it can do is cause agglutination. Again, we saw this with what reaction? with the blood typing, the mismatched blood typing. That's why we said whatever you are, you produce the opposite of what you are. So whatever your blood reacts with, clumps up with, is what you are. It has to be specific. Agglutination causes bacterial cells to stick together with the help of the antibody. And that's most of the time good, because what that does is it allows the phagocytic cells to find them all easily. You know, it's like you're putting the enemy all in one place so you can take them in all at once. What's the problem with this though? Yeah, I mean, in the case of the blood typing, you're gonna impair circulation significantly with something like that. We also see, like the formation of what we call immune complexes, where you have a big enough accumulation of antibodies and bacteria that phagocytic cells have a hard time handling them. They're large. They can literally clog up the kidney tubules and cause renal distress or renal failure. Strep is notorious for doing that, which is why you have strep, you're told to take your antibiotics like you're supposed to, because it tends to form those complexes. And then lastly, cellular cytotoxicity. Antibody-dependent cellular toxicity. What's going on here?
It's killing some
It who?
of the,
Yeah, so in this case, the antibodies, as they're supposed to, are alerting the other immune cells to the fact that there's a problem. Yeah. But in this case, it's not a phagocytic cell that gets there first, it's a natural killer cell. So the natural killer cells do have the ability to say, oh, well, you've got an antibody bound, you're gonna get destroyed. Are they phagocytosing that cell? No. How do natural killer cells do it?
There you go. Put holes in it and the granzymes in it.
Two chemicals, and the chemical names tell you what they do. Perforin, and then granzyme destroys it from the inside out. All right, questions about that?
Is when they bring in another, defense cell, like a phagocyte or a natural killer, trying to figure out how to ask it. I mean, that to me seems somewhat similar to like the chemotaxis and stuff like
It
that.
is.
Okay, so.
It is. The difference is that the antibodies are not releasing cytokines.
Right.
They are not
They
sending a,
themselves are the.
right, and the fact that they are present and bound is enough. Good question, good question. All right. So, we know about antigenic determinants, we know about antibody structure, we know about classes of antibodies and what they do, then we know the results of antibody and antigen binding, all right? Now, we're gonna deviate a little bit and talk about what happens when an antigen is phagocytosed with the cell-mediated response as opposed to the antibody one. All right, and that leads us to major histocompatibility complex, which is a mouthful of words for Ken, right? So we're talking about MHC. What is histone? Tissue, and compatibility means?
Are they compatible?
Are they compatible? What's it mean to be compatible with somebody?
We go well together.
You like them,
Complement each
you
other.
get along. Yeah, if you're histocompatible, it means that your tissues are similar, right? And in fact, that's how these complexes got discovered. MHC complexes or histocompatibility complexes are proteins. They're proteins that are present on the outside of cells. Some cells have one type, other cells have two, but think of MHC as a self-marker, all right? So they were discovered when people were tinkering and learning about organ transplantation. Who is the best person to get an organ transplant from? An identical twin, because you have yourself, really? Because I was sure somebody was gonna say a surgeon. I was expecting it to come from up there. I'm a little disappointed. What? It's not exactly the same, but with identical twins, they have the same DNA and they're gonna have the same complexes, same proteins on the cells. So they're the best candidate for a transplant. Well, anyway, as they were researching this, they started to notice about organ rejection and what was triggering that rejection, and it had to do with the self markers on the self cells. That's what the MHC is. So they're proteins, they're self markers, and they assist with cellular mediated immunity. So here's what I want you to remember, henceforth and forevermore, all right? When you see MHC1, I want you to know that these are present on all cells. I also want you to associate it with a particular type of T cell. In this case, which is it? Yeah, it's the cytotoxic T cell. MHC2 is associated with which? Yeah, with the helper T cells. And the way that I remember this is that the Roman numeral 2 reminds me of the two parallel sides of the H. It ain't much, but it's almost spring break and that's all I got. Alright, so these two things go together. From here, I can remember that the helper T cell is assisted by the CD4 protein. And again, I look at the two sides of the 4, and that helps me remember that that's H. Cytotoxic T cells is assisted. Yeah, CD8. And the reason I'm putting those proteins under the T cell is because these proteins are associated with the T cell. This is the protein that helps this T cell bind. Okay? So, MHC1, cytotoxic T cells recognize that as self. Every cell has an MHC1 complex, except one. Red blood cells. Why don't they? They don't need it. They're hemoglobin carrying machines. They don't need anything on the outside. So because all cells carry the MHC1, that means that the MHC1 is going to respond to endogenous antigen. Yes?
You said all cells have MHC1 separate.
And I can remember, what was the endogenous antigen? The floating one or the infective one? It's the infected one. So don't all cells have the potential to be infected?
Yes.
Yes, so that helps me remember, all cells can be infected. Therefore, their endogenous antigens, it's gotta be MHC1, cytotoxic T responds to that. Now down here, helper T's respond to MHC2, but not all cells have the MHC2 complex. It's the professional antigen presenting cells that have it. So cells like dendritic cells, phagocytic cells, macrophages, cells whose job it is to screen for and find invaders and destroy them. So I'm going to put APC here. Where do the antigen presenting cells live? In the lymph nodes, and the spleen, and the secondary lymphatic organs. Vault. That makes sense, doesn't it? Because that's where you want to be screening for pathogens in the first place. So MHC2, antigen presenting cells. Well, if you're screening for pathogens that are free floating, what type of pathogens are they? They are exogenous antigens. Did I see somebody's hand up a second ago? Okay, are we good with this? So let's say you have a cell in a lymph node and it is